Welcome, everybody. It's my pleasure today to introduce Andrea Guidolin, who will tell us about barcode matchings and p-norms of persistence modules.
Thank you, Henry. I'm very happy to be here to share some thoughts on barcode matchings, so I'm just going to jump into it. So today I'm going to present a construction of barcode matchings that are induced by morphisms, and this construction is different from the induced matchings of Bauer and Lesnick. Then I'm going to study the interaction between these matchings and p-norms of persistence modules. And at the end, I will show an application of this theory to a proof of Wasserstein algebraic stability. And what I'm going to tell is based on joint work with Jens Agerberg, Ren and Martina Scolamiero. We have a published paper, but a relevant portion of what I'm going to tell is also based on ongoing work with Isaac and Martina. So let's start with some preliminaries. Let K be a field. I define a persistence module to be a functor from the real numbers viewed as a poset to the category of finite dimensional vector spaces. And explicitly, a persistence module is a collection of vector spaces indexed by real numbers and linear functions indexed by pairs of real numbers. I'm going to call these linear functions the transition maps in these talks, and they satisfy that the transition from T to T is just the identity on XT, and the transition from S to T composed with the transition of from R to S is the transition from R to T. Then I define a bar, or it's also called an interval persistence module in the literature, as a persistence module supported on an interval, which means that the vector spaces are as follows. At T, we have a copy of the field K if T belongs to the interval and 0 otherwise. And the transition maps of these persistence modules are just the identity on K if both S and T belong to the interval and 0 otherwise. So here's a picture for a bar, which again is a persistence module in this talk. The bar starts at A and ends at B. I will denote it in this way with these brackets. And this is because we don't know what type of endpoints we have in the interval. It can be left closed, left open, and all combination of closed and open on the right as well. There is, however, a possibility of considering bars with endpoints that are decorated, which is what I'm doing here. So the endpoints will be real numbers decorated with minus or plus, and we endow this set with the lexicographic order. We also add a minimum minus infinity and a maximum infinity. And this is good because we have a bijection between pairs of decorated endpoints and intervals of the real line. I'm not going to be too precise with the decorations in this talk, but for example, when I say that two bars have the same endpoint, this will be same real number and same decoration. So more preliminaries, a multiset of intervals is a subset of intervals of the real line together with a function defined on this subset S to positive natural numbers. And it can be represented as just a set where we are considering the intervals. We are considering many copies of an interval according to their multiplicity. And we call this set barcode. Then a classical result in persistence theory says that every persistence module X can be decomposed as a direct sum of bars for some uniquely determined barcode B of X. And again, the bars can be written in this form, but in this talk, I will usually indicate which are the start point and end point of the bars. And just since we use the direct sum here, I want to recall that the direct sum of two persistence modules is defined pointwise. So at T, we just have a vector space that's the direct sum of xt and yt. And the transition maps are the direct sum of the transition maps of x and y. All right, a morphism of persistence modules is a natural transformation. So it's composed of many components, ft from xt to yt. And these linear maps have to commute with the transition maps of the two persistence modules. A morphism is called a monomorphism, or alternatively an epimorphism or isomorphism, if every map ft is injective or respectively surjective and bijective. And one last definition that we need is that of a matching between barcodes, which is defined to be a bijection between a subset of the barcode of x and a subset of the barcode of y. And in this talk, we will study matchings that are induced by morphisms of persistence modules. So let's look at some examples. The easiest example of a morphism between persistence modules are morphisms between bars. Here in the picture, we have two bars, and we have a non-zero morphism between them, represented by this arrow. We can have a non-zero morphism between bars exactly when the endpoints of the bars are in this order. And this can be seen, for example, by discretizing the parameter space and observing that a certain diagram commutes. So we do have a non-zero morphism in this case. If the two bars don't overlap in this way, we only have the zero morphism between the bars. So if the two bars overlap in this way, or if one is strictly contained in the other, we only have the zero morphism because commutativity of some squares forces the vertical maps to be zero. And since we have this picture, I can show what's the kernel of this morphism between bar is just this bar. And what's the co-kernel of this morphism between bar is just the spread bar. If the two bars coincide on the right, the kernel is zero, so we have a monomorphism. And if the two bars coincide on the left, we have a zero co-kernel, so we have an epimorphism, persistence modules, well, between bars. So let's look at slightly more difficult examples. In these examples, we look at monomorphisms. So the observation is that in general, co-kernels of different monomorphisms between persistence modules depend on the specific morphism that we're considering. For example, here we are fixing x and y. This first morphism maps the bar of x only onto the first bar of y, and this is the co-kernel. And we can observe that in this case, the monomorphism can be decomposed as the direct sum of two monomorphisms just between pairs of bars, where one bar is possibly the zero module. So in this talk, this is what I'm going to think of a matching a lot, most of the time. I will represent matchings as morphisms that can be decomposed into these simple monomorphisms or morphisms between individual bars. So in the other picture, we have a monomorphism where the bar of x maps to both bars of y. And in this case, the monomorphism G is not the direct sum of two monomorphisms between individual bars, as in the previous case. We can look at a slightly different example. It's similar to before, but now the bars of x and y, and all at the same point B. And this type of monomorphisms, where all the bars end at a certain point that is the same, I'm going to call block monomorphisms in this talk. So in this first block monomorphism, the situation is very similar to the picture in the previous example. It decomposes. The second block monomorphism also decomposes. In this case, the bar of x maps only to the second bar of y. But in this case, it's interesting to observe that up to isomorphisms, these are the only monomorphisms that we have between this x and y. So if I briefly go back to the previous slide, the situation where the bar of x maps to both bars actually falls within this this type of situation here in this case. It's basically because we can do a change of basis in y, which we couldn't do in the previous example. So this example is an instance of a theorem that we have, which is the following. It's a decomposition theorem for block monomorphisms. So if f is a monomorphism between two persistence modules whose bars all end at a common point B, then there is an injection basically between the barcodes such that f decomposes as a direct sum of these monomorphisms between individual bars, where some bars in the domain can be 0. And in particular, the cardinality of the barcode of x is smaller or equal to the cardinality of the barcode of y. This is just another way of saying that there is an injection. But also, we have a condition on the start point of the matched bars in this summons of the decomposition that comes from the very first example that I showed. If there exists a non-zero morphism between bars, then we know that the start point of the target bar is less than or equal to the start point of the bar in the domain. And in this picture, we have the general situation of a block monomorphism with these arrows representing these components of the decomposition. And we already see that we can interpret these arrows as a matching, which is what I'm going to do in this presentation. Here, I just wanted to mention that there are results related to this theorem in the persistent homology literature. One such result is in this paper by Jacquard, Nanda, and Tillman. They consider discrete persistence modules, while we consider pointwise finite dimensional, but they have a more general decomposition theorem because they are able to decompose arbitrary morphisms between persistence modules such that there are no pairs of nested bars. And in their decompositions, there is an additional type of summons, which are bars that map to 0. So for these block monomorphisms where all the bars end at the same point, we have this structure theorem that we can use to define a matching. So our next goal is to simplify more general monomorphisms to also read out some matching between the bars. This is a picture of a more general monomorphism. And what we want to do is to simplify it. And we will do it in a way that actually changes the morphism in this way. We will obtain a morphism that is different and usually not isomorphic to the original one. The way we do this is by looking at the arrows. There can be a bar that maps non-trivially to multiple bars in the codomain, but we want only to retain the arrows within the same block, where a block is a collection of bars with a common endpoint. So in other words, we want to disregard all the arrows between bars that end at different points. And the formal way to do this is to define a block diagonal operator that takes in a morphism between persistence modules X and Y and returns another morphism between the same persistence modules X and Y. This is called the block diagonal operator, delta. And it's defined as follows. We regard the space of morphisms between X and Y as a direct sum of Hom spaces of morphisms just between individual bars, which, by the way, allows us to think of morphisms as certain matrices with entries in the field. Then we project this direct sum into a smaller direct sum with less summands, where we just keep the summands corresponding to pairs of bars with the same endpoint, bi equals dj. And doing so, we obtain this modified morphism delta f. Again, for a monomorphism f, this is what we're actually doing. We are forgetting about this arrow that connects bars with different endpoints. The name block diagonal operator comes from the fact that if we view morphisms as matrices, what we're doing is we're keeping only the diagonal blocks of these matrices, which correspond to bars with the same endpoint.
Andrea, can I ask a question?
Sure.
So if no two bars have the same endpoint, then this is the zero morphism?
It's interesting in our situation for monomorphisms, and in that situation, you know that there are pairs of bars with the same endpoint.
Ah, I see. So each bar has to either map to zero or map to at least one bar with the same.
Exactly.
I see.
But you're right. The definition is general, and in that case, for morphisms where you don't have pairs of bars with the same endpoint, you would get the zero morphism. It's just not a very interesting definition in that case.
Right.
But for monomorphism, it's interesting. Yes, and this block diagonal operator has some interesting properties. It's linear, it's functorial, so it behaves well with composition of morphisms. It preserves direct sums of morphisms. It also preserves monomorphisms, meaning that if F is a monomorphism, then delta F is also a monomorphism. But as I said, possibly a different one, a non-isomorphic one. But however, if F is one of the spatial monomorphisms, which are direct sums of monomorphisms between individual bars, plus morphisms between 0 and 1 bar, then delta F is equal to F in this case. So to summarize, our strategy to define matchings is using this delta operator to, given any monomorphism, transform it into a simpler monomorphism, which is the direct sum of block monomorphisms. So we start from any monomorphism, and we obtain a monomorphism, which is direct sum of block monomorphisms. And for these block monomorphisms, we can use the structure theorem that I stated before. So we do have a matching for each block, which gives us a matching for delta F. And that's the matching that we associate to a monomorphism F. So it's time to also define to state the definition of the induced matchings introduced by Bauer and Lesnick. It's based on a theorem called the structure theorem of persistent submodules that can be viewed as a consequence of the decomposition theorem of block monomorphisms if we apply it to the monomorphism delta F. And I'm going to read this theorem just to observe that it's actually similar to what we did in the structure theorem of block monomorphisms. I'm going to use the original notation by Bauer and Lesnick to indicate the intervals in a barcode that end at a fixed point B. So the theorem says that if X and Y are persistence modules, and if there exists a monomorphisms from X to Y, then for each endpoint B, the number of intervals in X ending at B is less than or equal to the number of intervals in Y ending at B. And there is an injection between the barcodes of X and the barcode of Y, which sends for every B the ith largest interval of X ending at B to the ith largest interval of Y ending at B. And these two paired intervals satisfy that A prime is less than or equal to A. The picture for this theorem is this one. Now it's a matching between barcodes. It's not a morphism, but we can see these arrows also as a morphism that maps this bar to this bar, this bar to this bar, and so on. And indeed, we will do this. And there is one unmatched bar in this case in Y. So we have defined two types of matchings for monomorphisms for now, and let's revise them. So in our case, we construct this block diagonal monomorphisms just by forgetting about the arrows of the original monomorphism that go across blocks. So we apply this delta operator, and from these blocks, we can define the matching by using the structure theorem of block monomorphisms. And in the same situation, the matching by Bauer and Lesnick maps the largest bar to the largest bar, the second largest to the second largest, and so on. And I stated everything for monomorphisms, but there are dual results and constructions for epimorphisms. I'm not going to state them here. I just prepared some pictures that I hope look dual enough to the ones for monomorphisms. All right, so we have defined these two types of matchings for monomorphisms and dually for epimorphisms. So we want to define them for arbitrary morphisms of persistence modules. The strategy to do this is the one used by Bauer and Lesnick. We use the canonical factorization of the morphism F through the image. So we have an epimorphism onto the image and then a monomorphism from the image to the codomain. And for the epimorphism and the monomorphism, we can define, for example, the canonical matching by Bauer and Lesnick. And the induced matching for an arbitrary morphism is just defined to be the composition of these two. And we do the same for our matching. We have a definition of the matching for the monomorphism and for the epimorphism, and we define the matching for the arbitrary morphism to be the composition. Again, let me remind you that we can view a matching, an induced matching, algebraically as a monomorphism, as a morphism that decomposes into parts which are morphisms between individual bars. Again, I'm going to do this to regard these matchings in a more algebraic version between persistence modules. Okay, it's time to compare the two constructions. Our matching mu is additive, which means that the matching induced by a direct sum of morphisms is the disjoint union of the two matchings. And here's a picture to represent that. The picture is, again, in the case of bars that have the same endpoint, just because previously I showed you many examples of that situation. If you take the direct sum of these two morphisms, the matching doesn't change. It still matches the first bar to it coincides with the original one. However, our matching is not functorial on monomorphisms and epimorphisms. And I want to note here that there is another matching that has been studied by González Díaz, Soriano Trigueros, and Torras Casas that has very similar properties to ours. So in the future, we actually plan to compare our matching with theirs. The definitions are not very similar, though. So the induced matching by Bauer and Lesnick has different properties. It's not additive, and here is a picture showing why. That has to be compared to the previous situation. Here, if we take the sum of this morphism and this morphism between bars, the matching actually changes because the rule is matching longest bar to longest bar and second longest to second longest. So it's not additive for this reason. However, it's functorial on monomorphisms and epimorphisms, which is also a useful property. All right, in the last part of the talk, I will consider a different type of comparison for the matchings, and I will also compare them to the original morphism that induces them. And this is a more quantitative comparison, so to speak. I want to consider a measure of the quality of a morphism and of the induced matchings. So let's say that our goal is to assess the quality of a morphism between persistence modules, where by quality, I mean how far a morphism is from being an isomorphism. For example, in this picture, we have a morphism from X to Y, where also the image and the co-kernel and kernel are displayed. And we see that there's quite a big co-kernel here. So maybe we can think that this morphism is not very close to being an isomorphism. And there's at least one way to make this rigorous, which is using p-norms of persistence modules, which are defined as follows. Let Z be a persistence module, which has a certain barcode decomposition. We define the p-norm of Z as the sum of the lengths of the bars to the power of p, and then we take the pth root of the sum. We do this for p, for finite p. For infinite p, when p is infinity, we define the infinity norm of the persistence module to be just the length of the longest bar. So this is the p-norm of any persistence module. We use the p-norm to define the notion of p-cost of a morphism, which is defined by considering the p-norm of the kernel, which is a persistence module, the p-norm of the co-kernel, which is a persistence module, and then we combine them, not taking the sum, but taking the p-norm of this two-dimensional vector. This is the definition of p-cost for morphism. So we want to see how morphisms and matchings interact with this notion of p-norms and p-costs. We have a theorem, which I'm going to state again for monomorphisms, which is the following. Let F be a monomorphism between a persistence module X and a persistence module Y. Then the p-norm of the co-kernel of this monomorphism is larger than the p-norm of the co-kernel of the morphism associated with the matching mu that we defined, which in turn is larger than the co-kernel of the morphism associated with the matching defined by Bauer and Lesnick. So we have these inequalities between the p-norms of co-kernels. We have pictures here. This is the original monomorphism. Here it's simplified. and we have our matching. Basically, we delete this arrow. And here we have the matching by Bauer and Lesnick. And the three co-kernels are displayed. And the claim of the theorem is that the p-norm of this one is larger than the p-norm of this one, which is in turn larger than the p-norm of this one.
Andrea, can I ask a question?
Sure, go ahead. Yeah.
The two matchings, the mu and the xi matching, do they always have the same one norm?
Yes. Yes.
Thanks.
Yeah, and we have a dual theorem for epimorphisms, where you just replace monomorphism with epimorphism and co-kernel with kernel. We actually stated these theorems in the article that is published. They were stated for tame persistence modules. Now we have a different proof for the more general case of pointwise finite dimensional persistence modules. And I want to just briefly tell you about the ingredients of this proof for this theorem for monomorphisms. We can use two propositions to prove this theorem. The first one is the following. Let F be a monomorphism between X and Y. And let's consider just two parameters, S and T, two real numbers. Then we have these inequalities between ranks of the internal maps, of the transition maps of the co-kernels. So the rank, the dimension of the image of the transition map from S to T of the co-kernel of the original morphism is larger than the rank of the transition map of the morphism induced by our matching, which in turn is larger than the rank of the transition map of the morphism associated with the Bauer and Lesnick matching. This is still non-trivial to prove, but it's easier than proving this inequality for p-norms, because we're considering just two fixed parameters here. So it's a bit easier. And here are pictures representing these inequalities. In the first case, the rank is 1 because we have one bar going across. The rank of the co-kernel associated with our matching is also 1. We have this bar that goes across. And the rank of the co-kernel of the Bauer and Lesnick matching is actually 0 here because there's no bar going across. So this is an example for this inequality. If we slide T over to the end of the long bar here, we see that this is an example for also this inequality, the first one. So yeah, we proved this proposition for the rank invariant. And then there's another proposition that says the following. Let omega be the set of pairs of real numbers such that the first one is less than or equal to the second one. Fix some p between 1 and infinity, and consider a function gp defined on omega by this expression. Then for any persistence module x, if we integrate over this domain omega the rank invariant of x multiplied with this function gp, we obtain exactly the p-norm of x raised to the power of p. So this is a relation between the p-norm and the rank invariant. And it's quite useful because together with the previous proposition, we can now just integrate the rank invariance of these co-kernels over omega multiplied with this function. And we obtain the claim by monotonicity of the integral. And yes, we wanted to actually consider p costs, not only p norms of modules. P cost of a morphism is defined using, well, combining the p cost of the kernel and co-kernel. And now we have a proposition which is an easy consequence of the theorems that I showed before for monomorphisms and epimorphisms, which says that the p-cost of any given morphism is larger than the p-cost of the morphism associated with our matching, which is larger in turn than the p-cost of the morphism associated with the matching of Bauer and Lesnick. And this consequence is proved just by considering the factorization of the original morphism. The kernel of F is the same as the kernel of this epimorphism. The co-kernel is the same as the co-kernel of this inclusion. And now we replace the monomorphism and the epimorphism with the matchings, either our matching or Bauer and Lesnick's matching. And by the previous theorems, we know that we can only decrease the p-norm of the kernel and also of the co-kernel in this process. So this simplification of morphisms in terms of matchings is actually very well behaved with respect to this notion of p-cost. It decreases the p-cost. All right, and I have just a couple of slides to show you an application of these theorems. The application is to the so-called Wasserstein isometry theorem. So I want to introduce two different types of Wasserstein distances. One is the usual one. So if we have X and Y persistence modules, we can consider the usual combinatorial Wasserstein distance between the barcodes, which is defined by looking at matchings, which I here represented as matchings between persistence diagrams. This is the usual definition. It has parameters P and P because we're comparing points on the plane with the p-norm, and then we are also combining the costs with the p-norm. But we can also define an algebraic Wasserstein distance. Scraba and Turner did this in their paper, which is it's a distance between persistence modules, and it's defined as the infimum of a set of real numbers C that are associated with pairs of morphisms from a third persistence module Z. One morphism goes to X, one morphism goes to Y, and the cost C of such a pair of morphisms is defined to be, well, the P cost of X and the P cost of G, again, combined not by taking the sum, but by taking the p-norm. So this is the algebraic definition of a distance that is called the algebraic Wasserstein distance. And Scraba and Turner have this theorem that says that the algebraic Wasserstein distance between persistence modules coincides with the combinatorial Wasserstein distance between the associated barcodes. So in the very last slide, I wanted to show how we can use matchings to prove the difficult inequality in this theorem, which is called the algebraic Wasserstein stability. We can actually use the induced matchings by Bauer and Lesnick to do so. The inequality is that the algebraic Wasserstein distance is larger than the combinatorial one between the associated barcodes. So to prove this, since both distances are defined as the infimum of some sets of costs, we can prove that given any pair of morphisms from a persistence module Z to X and to Y, we can construct a matching between the barcode of X and the barcode of Y with a cost smaller than the cost associated with this pair of morphisms, right? So the very first step of this proof is replacing the original morphisms with the morphisms associated with the canonical matching by Bauer and Lesnick. And by our previous theorems, we know that the p costs decrease So this pair of morphisms has a cost that is smaller than the cost of the original morphism, pair of morphisms. Now the rest of the proof is basically manipulating a little bit this pair of morphisms, but we are already in the domain of combinatorics now because we were considering matchings, not arbitrary morphisms. So it's kind of easy to do these manipulations. The key step was reducing from arbitrary morphisms to matchings. And yes, exactly. Once we've done these manipulations, we can just define a matching from X, from the barcode of X to the barcode of Y by composing these two matchings. All matchings are invertible. So we obtain a matching that has the same cost of this pair of morphisms, which had a smaller cost than the original pair of morphisms. So yes, this is how one can prove the algebraic Wasserstein stability. All right, just a few conclusions. Matchings induced by morphisms can be understood in terms of simplification of monomorphisms and epimorphisms, which is what led to our definition and also Bauer and Lesnick's. This process of simplification of monomorphisms and epimorphisms, we saw that it interacts well with a notion of cost based on p-norms. And finally, we observe that such well-behaved induced matchings can bridge between algebra and combinatorics, and this can be important, for example, applied to the algebraic Wasserstein distance. It could be very much non-trivial to compute such a distance defined on the minimization of costs of pairs of morphisms. But once we know that we can replace the morphisms with matchings, suddenly it becomes computational, this definition. So matchings are this bridge between algebra and combinatorics. And with this, I thank you for the attention.
Thank you very much. So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. All right. Questions? I'll start. So is there a brief word you could say about how Turner and Scraba originally proved that inequality, or is it sort of too complicated to say?
The inequality of costs. Yes, they have a strategy which is slightly different. So the general scheme of the proof is the same. The difference between our approach and theirs is how one proves this inequality for the costs, right? So in our case, this is a consequence of these theorems, which study the interaction of the p-norm with monomorphisms and epimorphisms, and with these simplifications in terms of matchings. In their case, they have a strategy that is more related to an interpolation definition that is closer to an interpolation strategy.
Mm-hmm.
Yeah, so it's slightly different, but the general scheme of the proof is the same. This was an example of an application where we can use these inequalities, which are convenient, and for us, they are a consequence of these theorems.
Great. Further questions? Let me ask another question. It's maybe not so relevant to what you discussed in the talk, but I'll ask it anyway. So, um, I mean, you described connections between combinatorics and algebra, often in an LP sense, where P didn't need to be infinity, right? And so I wish I knew this better, but for like P equals infinity, you can relate both combinatorics and algebra to geometry, like the stability of sublevel set of functions on a space with, the L infinity metric or, interleavings of rips or check. Do you know have these LP notions been connected to geometry?
Oh, it's interesting. Um, yeah, no, I've never thought about that. I never thought about that. Um, yeah, um, I know that exactly as you mentioned, for P equals infinity, there is this interleaving of sublevel sets,
Hmm.
which algebraically gives you an interleaving of persistence modules, which in turn can be used to define the interleaving distance.
Right.
Um, the algebraic Wasserstein distance for P equals infinity coincides with the interleaving distance. Um,
Mm,
yeah, this can be seen in a few different ways, but yeah, for different P's, it's unclear to me. Yeah, it's unclear to me what happens geometrically with sublevel sets of functions.
right. Any further questions? Well, if not, thanks so much, Andrea, again, and let me stop the recording here.